how was your exam? Was it what you expected, or total surprise, or no opinion? So as I said, the format of exam may look different, but the content is, believe it or not, is the same, exactly the same. So I prepare answer key sometime this week or early next week and go over those questions together, okay? Right. This week, starting from this week, we will first start discussing multivariate time series model. So we have more than two series, more than one series in a model. We will learn first basic model known as vector autoregression bar. So this is basically autoregressive model. So the same as autoregression in a single time series model or univariate time series model. But now the dimension is vector, okay, multiple time series. But when you deal with multiple time series, if the dimension increases, you may face some problem because of larger dimension of the problem. So we'll learn something called principal component analysis. This is one way to reduce the dimension of the problem when you deal with many time series at the same time. Okay, so basically this one is going to be used to generate short-term forecast and similarly this one. And later, when we cover this subject, we'll extend this multivariate time series model to something called vector error correction model. A vector error correction model. This one share similar structure as vector autoregression, but it has some other feature than this one, and primary focus is to generate a long-term forecast. Okay. And when we cover up to that point, then later on during this semester, we will learn some other extended model like state space model, and regime switching model, and other topics. Okay. So these are what's ahead. Okay. So let's start with some motivation here. This time series has been introduced previously. Basically, this is zero coupon bonds, or sometimes it's called discount bond. Is the one that makes only one payment at a date of known maturity. Okay. So if you look at, let's say, particular month, and there are several points, right? several points. So in a particular day, this is maturity. This is spot rate. Then it may look more or less like this curve. Okay? So we are looking at this particular cross section. Okay? Similarly here, right? But as you can see, the longer maturity and short maturity spot rates, if the dispersion is big like this, then it means it is quite steep. Okay? And if you see some other periods like this one or that one, the gap is very small, right? That means the spot curve is flat. Right? And our task is, sometimes you may want to generate a forecast starting from known time and to the future. Right? So how to predict? Well, previously, univariate time series modeling framework, you pick single series and fit, let's say, ARIMA model, and then you can generate forecast for the particular series, right? But this time, what you are interested in is what is this spot curve, let's say 3 months from now. Will it be here or here, or will it be steep or flat, right? So that's our task. Okay? It shows particular maturity like 0.25 year, half a year, 3/4 years, and 1 year, 1.5 year, 2 year, 2.5 year, and so on. Okay? So different maturity, and for each maturity you have series. So if you look more of these maturities, you have more series, right? So you have more series to work with to generate forecast, right? So dimensional problem is now getting bigger and bigger, right? So we'll learn how to handle this because we'll be actually we'll try to forecast this one as an exercise. We need to learn a little bit more about bond here. So as I said, zero coupon bond have only one cash flow. Okay, so from now, which is T, N is the year, for instance. So if N is 10 years, then this cash flow one occurs at the end of period 10 years. Okay? And what is the price for that at T? So this cash flow is generated 10 years from now, right? But what is the value of that today? Okay? So if you know some appropriate discount rate, then you can discount, because this is annual rate, so you can discount this one using this rate, N-year spot rate, by 10 years. Then that will give you this number, right? So, of course, there is no such bond that generates $1 in 10 years and traded now. So this is kind of a hypothetical bond, but there is a trick that allows you to actually calculate either this one or that one using transaction data. Okay. So suppose someone did that. So this is the one for, let's say, 10-year, 3-year, 1 year, and so on and so forth, as is depicted in this one. Okay. So if you happen to know this number, then what is the value that gives you, let's say, 25 after 10 years? Right? You can discount this one using this 10-year rate available at T. Okay? If you have cash flow after 5 years, this amount, then appropriate discount rate is going to be 5-year rate, spot rate, available at T. Right? So these are a particular date T, this curve. Right? This curve. There's a simple algebra saying, if you actually take natural log on this one, bond price, and natural log of 1 plus y, small, this one, there's a relationship like this one. So maturity is known, usually known. So if you know this number, then you can calculate this one, or you can recover price, right, using this relationship. So historically, this is in terms of two-dimensional graph, but you can see the same thing in three-dimensional graph. So this could be time axis, and this could be maturity. So you can see that sometimes it gets steeper, flatter, right? So actually, you are trying to forecast kind of surface of this surface. Well, then what is spectral autoregression? The representation is basically the same as ARP process. I didn't express it as a deviation from mean, but you can express this one as a deviation from long-term mean, or like this one, intercept term. Only difference is now x is a vector. Okay, vector. So if you have n vector, so number of variable is n, then this is m vector, and then this one, intercept term, has to be consisting of n constant, right? And this A1 is now n times n matrix of coefficients, right? N times n, because there are n number, so to make it equal dimension, so you have to multiply n by n, right? So a xt minus 1, this is n by 1, and this has to be n by n, right? So make this dimension n by 1, right? So n by 1, n by 1, n by 1, right? So also this one, n by 1, like this one. Usually, expected value of these residuals are, as usual, 0. And covariance matrix is omega. Okay, omega. When T and S are the same, okay, so we say this covariance matrix as a contemporaneous covariance matrix. And we usually assume that if this T and S are different, and we usually assume that covariance is 0. Okay. So simplest case is when P is set equal to 1. Okay. So this is the example of VAR 1. Okay. one way of rewriting VARP is to use a lag operator like this one, where A of L polynomial is defined in this way. Previously, when we talk about univariate autoregressive process, we say this polynomial is the polynomial in lag operator L, right? But that's scalar operator. In this case, because A1, A of P, all they have dimension n times n, right? So this is now matrix. So this is not one unity. This is identity matrix of dimension n, right? So we say A of L is the matrix polynomial in lag operator L. This is a function of L, right? In this way, to the power 0, 1, up to P, right? So L is just scalar, but these are matrix. So the whole thing becomes matrix polynomial, right? So, similar analogy can be applied to, let's say, what is the stationarity condition of, let's say, ARP process, VARP process? Very similar, replace L by Z, unknown Z, and if coefficient matrix are given, then you can take determinant set equal to 0 and calculate all those roots Z and see if whether those roots lying outside unit circle. Okay? Outside unit circle. So basically you can do that, but the computation is a little bit more complicated. And also, when we actually write VARP model in this way, even though it is a single equation like this one, but basically it consists of set of n equations, right? So x1t equals to, x2t equals to, up to xnt equals to, right? So there are n equations, right? How to estimate then those coefficients? Well, because this is a vector, you might think that, well, there may be some other method, but basically, when we learn basic multiple time series multiple regression analysis, what is known is if you have a set of equations or system of equations which consists of equation that sharing same set of regressors for each and every equation. In that case, you don't have to worry about the dimension. You can just apply least square method to each equation. So usually the estimation of these coefficients are done by equation least square, which is very simple. Okay. Of course, if you want to estimate this model using maximum likelihood estimation, then you have to make some assumption about this one. For instance, E of t is distributed multivariate normal with mean 0 and covariance matrix sigma. Okay. But that's going to be a very difficult problem because if you want to maximize, let's say, likelihood function for this problem, you have many parameters to be estimated here and many parameters estimated here, right? So it's going to be a very big problem and very difficult to get converging estimate. But if you run a regression, each equation by least square, then that's a very simple estimation problem, right? So estimation is, question? No? Yeah. Estimation is done by equation, least square, and we'll see the example shortly. Okay. So basically, the reason why we consider, let's say, monthly stock return and bond returns in a bivariate setting like this one is, well, as I said, if you apply just a univariate time series model, then you're working with the single series like this one or that, right? But as you can see that, stocks and bonds are traded in the same capital market. They could be, they compete each other, or sometimes they could be complement each other, right? So one of the benefits of using this VAR type model is to use the correlation between these two series. Or in economics, we say things are determined simultaneously. Or we say stock prices, bond prices, and other major macro or financial time series are determined jointly. Or we say endogenous, right? There has been long debate in economics. Say money supply triggers change in output, and it triggers changes in, let's say, money demand, and so on and so forth, right? So this is kind of causal chain. So increase in money supply, increased output. If you think it that way, then that's causal relationship, right? But the other view is, interest rate, money demand, output, foreign exchange rate. These are determined simultaneously, jointly. In that case, it is all endogenous, right? So in our case, endogeneity is introduced here. So if you have set of variables like this one, okay, so that's x, and it has an error term, right? And covariants are usually non-zero, right? So endogeneity is introduced to this model by having non-zero covariance here, right? And also dynamics is, these are all common to every element in vector x. And so not only its own lag, but also the lagged dependent variables included in this vector also affects, let's say, x1t. So x1t is determined by its own lag and lags of other variables like x2t minus 1, x3t minus 1, and so on. Right? So in that way, correlation is determined, and also endogeneity is introduced in this part. But we don't know whether, well, in fact, increase in y caused more money supply and this and that. We don't know this, right? So we are not going to claim anything about this one. But somehow we try to find some model that allows you to exploit the correlation structure among this set of variables. So that's the main motivation. So typically, we've seen this one previously. a large capital stock, and that's stock index, this one, and long-term government bond, so this is bond index, right? And these are typically non-stationary time series, right? So in a typical, the starting point of vector autoregression, when you try to generate a short-term forecast, we first make sure that things are stationary, right? So instead of working with index, stock index, bond index, we take log difference to make it stationary. Okay, so stationary time series. This is time horizon. Right? If you actually look at, let's say, the combination of consumption and Y in year 70, 71, 72, 73, and so on. You know, if you look at this way, when we say short term, it means this term. If Y changes, what happened to this? But when we say long run, this relationship. Okay? So basically what we are interested in is we want to forecast C and Y. Okay? And long-term forecast means in somehow we want to stay in this line. So perhaps this one. But when we say short-term forecast, it means this particular short period movement. Okay. So by building VAR model, you are looking at very short sample, short horizon. But when we introduce this one, and we'll look into longer horizon. Okay. So there is a long-run relationship like this one between some variables, as well as short-run dynamics. Right. So if you have both, and this is the model. If you are looking at just this short movement, then that's VAR. Okay. So first thing, change in index. So this part shows, well, we are now talking about this situation, right? This situation. How to do it? I'll show you with real example. So I uploaded one sample data called VAR 8 work file 1. So there you can find these data. Okay. There you can find some variable like F1, 2, 3, and we'll call this one as 3 factors of the term structure of spot rates. So in a spot curve today, tomorrow, day after tomorrow, it will vary like that, right? But as you can see, you know, the shape of this spot curve is basically determined by, well, where this curve lies. Like this high, this high, and this high. So that's what we call level factor. Level. So if level factor increases, expected to increase tomorrow, then the whole curve will more likely to shift up, right? Right? So the first one is the level. The second factor is, well, it may shift in a parallel fashion like this, or it could be like, you know, the longer maturity spot rate rise faster than short maturity spot rate. So it could be steeper, right? Steeper. Or sometimes it could be the other way around, right? So second factor is what we call a slope. And slope is determined, usually measured by the difference between long rate and the short rate. So this is slope, this difference. Some arbitrary long maturity spot rate and subtract short maturity, arbitrary short maturity spot rate. That's your, you know, definition of slope. Okay? And the third one is this curve could be straight line, or it could be curved, or it could be curved the other way around. Right? So we call this factor as curvature. So even though the movement of spot curves over time look very complicated, but basically the location of, it has been known that the location of spot curve is basically determined by these three factors and perhaps some other minor factors, which is kind of trivial. Okay? So in somehow, when we actually learn this space model, I can show you how I get these three as F1 and F2 and F3. So particular point in time, let's say this curve, this particular curve is determined by particular value of level, slope, and curvature. And particular day, this one is determined by particular values of this. So if you calculate those three numbers each point in time, then you can find some series, right? So that's what I got here as three factors, F1, 2, 3. And in this example also, I have several other variables like nominal exchange rate, NEX, and oil price. This is Brent oil price. And some others like real GDP, seasonally adjusted, CPI, GDP deflator, core rate. Okay? This is short-term interest rate, right? So I tried to build some model using this one. But first, let me try what is known as macrofinance model, which is very similar to the simulation model adopted by our Ministry of Strategy and Finance. Okay. So this is VR8 work file 1. I uploaded, and you can see data start from the second quarter of 2000 and all the way up to third quarter 2011. And also you can extend it, of course. and I have range up to 2016. So if you want to generate forecasts beyond this period, then you can store that. And here is a call rate, CPI, and nominal exchange rate, real GDP, seasonally adjusted, oil price, and so on. Okay. Vector autoregression is very simple. So let's try to, this is a typical output screen of vector autoregression. So to generate this one, let's say it says using sample up to this point and these variables. Okay, first let's just consider these are data of your interest, and we'll try to go through the mechanical aspect of VAR estimation. Okay, and then we come back to this specification and why this may be interesting exercise. Okay, so first, there's a quick estimate VAR, right? Estimate VAR. So let's try to set the sample to 2010. So let's leave last 4 observations as out of sample. Okay. And it says unrestricted VAR, and so this is basically VAR specification, and if you choose this one, model becomes this one. Okay. For the time being, this, and it asks what is the endogenous variable, because as I said, we are modeling this short-term forecasting model as a stationary, multivariate stationary time series. So we have to make sure all these elements in vector X are stationary. Okay. It is common. The common assumption made in the literature is the level series is stationary. Slope is also stationary, and this one also stationary. And actually, as I said previously, many economic and financial time series are non-stationary. GDP, stock price. Right? But interest rate. But interest rate is, well, if you apply formal ADF test, it is non-stationary, of course. Strong evidence of non-stationarity. And if you, well, in many economic and financial time series, if you don't distinguish the difference between stationarity and non-stationarity, and your empirical result will be very different. That's typically the case. Whether you use GDP as a level, original data, or convert it to growth rate, depending upon which one to use, your regression result will be very different. So you will know exactly, by reading some output, you can see that you can easily know or guess your specification is incorrect because of your negligence about stationarity or non-stationarities. But the interest rate, this is very interesting variable. In many applications, sometimes even if you forgot to make it stationary, result doesn't seem to change that much. This is very much kind of magic. But the thing is, if treating something as a non-stationary is correct, why don't we stick to that? Like, if you are dealing with interest rate, just take difference, make it stationary, and go from there. But why sometimes people assume that, well, the interest rate itself is stationary time series, although ADF test statistics suggest otherwise. The reason being, many interesting interest rate modeling papers assume that there is a long-term average or mean in the interest rate process, like a Baschek process or Cox-Ross Ingersoll process, a square root process. Many of those interesting model assumed in interest rate modeling literature, they all assume that interest rate is more or less stationary in the long run. So even though as a student who takes this time series class, you may wonder why we sometimes treat interest rate as a non-stationary variable and sometimes ignore it and treat it as if it's a stationary time series. You may wonder, but interest rate is the only exception, I think. But sometimes it works very well. So here I try to include endogenous variable. By that, what I mean is what has to be included in this vector x. Okay, so I try to put this one, but assuming all are stationary. So here, first one is F1, F2, F3 as it is. So I type it as it is. 3. Now the fourth one is D log real GDP SA. So this is GDP growth rate, right? Which is stationary, right? So D log SA. And then CPI. So D log CPI is CPI inflation, which is stationary. And this one is the one, core rate. This is interest rate. So this is a short-term overnight core rate. So borrowing rate between banks, right? And if you apply Dickey-Floor test, and this is non-stationary, but we follow the typical convention in the industry, so we just use core as a stationary variable, okay, without differencing it. Okay, then exchange rate, nominal exchange rate, we convert it to rate of change. And oil price is also non-stationary, so D log oil price. Okay, and this one lag intervals. So it asks what is the value for P. We don't know yet, so you can try. Let's say 1 means VR1 model. If you type this, you have one more lag. So P is set equal to 2. And you can set it to 3, 4, 5, right? So if you have quarterly data like this one, usually, maximum lag could be 1 to 4. Usually, short-term dynamics lasts about a year or less, right? So probably you will find some magic number from 1 to 4, not exceeding that, right? So let's try this. And the C means intercept term is included, okay? So this is all we need to specify. Very simple. So let's try this one. So this is the output. So these 8 variables are x, okay, vector, right? First variable. And vector autoregression is, this one is regressed on its own leg and others leg. So leg 1, 2, leg 1, 2, 1, 2, and then others leg 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. The second variable is regressed on its own legs, and also the same other legs, right? So structure is exactly the same, right? But of course, coefficients are all different, right? So first one is coefficient estimate. Second one is standard deviation. The third one is t-statistic. So if you look at this one, significant. This one about marginally significant. Marginally. If you take, let's say, 5% or 10% as threshold, about 2 in absolute value, 2 that's 95% significant, or 1.64 in absolute value, that's about 90% significant. So you fit this model. And as you can see, some of them are significant, some of them are marginally significant, and some of the significant and insignificant, right? So there are many things mixed. And if you look at the first equation, adjusted R squared is about 81%, 84%, 29%, and others like 42%. This is negative. So nothing explains that, right? Typically, when you have negative adjusted R squared, that means this sequence is not being explained by anything. It's just purely random, right? This one, 0.94. This equation is for core rate. Because we think that's non-stationary, but we are treating it as a stationary variable. So it's like, if you run a regression of stock price on its own leg, then R squared is very big, right? So this is typically the similar situation here, right? So hopefully you're not be that thrilled by finding this big R bar squared in a core rate. That doesn't mean that you can predict it with very good precision. It's kind of screwed up in your specification. But people accept this. So let's leave it there, and others about 20%, about 20%. Okay. But as you can, as I mentioned, you can estimate this one as a equation by equation least square. Very simple, right? You can generate this output in a split second, right? So very simple. But how many legs would be better? VR2 or VR1 or VR3? Which one? So we can apply our analogy, borrow some analogy from univariate analysis, where we use information criterion, right, to compare competing models, right? So where is our information statistic? Below here. Archaic information criterion minus 42.2. compared to, let's say VR1. Minus 42.0. So which one is smaller? VR2, right? VR2. How about Schwarz criterion? Minus 39.0. Minus 39.0. VR2. Minus 36.4. So in this case, VR1 is better, right? VR1 is better. So what it says is, Schwarz criterion says VR1 is a better model, whereas a Kaike information criterion, it says longer legs, right? But actually, if you increase number P from 2 to 3 and 4 and 5, what happened probably in this setup is this is going to be getting smaller and smaller as you increase P. That means you are not finding optimal P. But probably if you keep track this Schwarz criterion for P equals to 1 through, let's say, 4, then it's going to be minimized at leg 1 and then increase. So finding minimum, right? So if you do this exercise and as you increase P, if you find this number gets smaller and smaller and smaller, and that doesn't necessarily mean that more legs are required. But simply, a Kaike information criterion is confused. It's not finding optimal leg, right? So my preference, particularly when I work with Korean data in this kind of setting, I prefer using Schwarz criterion instead of Kaike information criterion. But it's all up to you. You can, as I said, there are many different information criterion, like Bayes information criterion or others. So as long as you stick to one measure and consistently compare the result, then I think you're fine. Okay. And now, why we are interested in this type of model? Well, let's take a look at let's see. Let's put this thing back to VR1. Okay. Let's think about whether you can, make some sense out of this result. The F1, as I said, is the proxy for level, right? So it determines the level of this term structure, right? This is the call rate 1 quarter ago, right? So, if you are looking at particular term structure like this one, this short end, this rate is more or less call rate, policy rate. Right? Call rate is the one that mature overnight, right? Next day is due, right? So very short maturity. Monetary policy is about determining this point. policy rate. Currently, it's 2.75, 2.5 or 2.75. Either one, right? 2.5, I believe. But about that rate, right? Suppose what is likely to happen if they increase policy rate from 2.5% to 2.75%? Location is more likely to shift up, right? Shift up. So it says coefficient is positive. T value is not strong, but 1.8, it has some meaning, right? At 10%. So, if core rate increase 1/4 in the previous period, then it's likely to shift this thing up. And how about inflation rate? If CPI inflation increases 1/4 ago, what is likely to happen to the location of this curve? Well, it says to the opposite direction. So maybe, if inflation was high 1/4 ago, then the monetary policy regime may want to squeeze the money, right? So well, it may walk that way or the other way around. But this is not the contemporaneous relationship. Nominal interest rate is real rate plus expected inflation. So if inflation rises, nominal rate increases, so shift up, right? But this is a lagged relationship. So there may be something other going on. And the prediction, according to this model, is that inflation was high previous quarter, then the level next quarter is going to be going down, right? So maybe you can build some story behind this one. So very similar. You see, if economy was good, growth rate was good, and slope gets bigger, positive, right? So if current economic condition is good, turned out to be good, then 1/4 later it is expected that this curve gets steeper. And also it is known that the term structure, particularly this variable, is a leading indicator of economic conditions. So in the current period, if this curve is reversed like this one, this way, so the sign of slope changes from, let's say, positive to negative, right? Then that is usually interpreted as kind of upcoming recession, usually like 2/4 ahead. So in the United States, typically, if term structure this quarter gets flattened or even reversed, then usually, on average, in 2 quarters later, economic downturn starts. So in somehow, there's a literature relating slope variable and real variable like GDP. So this is included as one of the elements in your vector X. Right? Similarly, we can we can build any kind of story, but many people think that inflation and short rate or policy rate, exchange rate, and exogenous factor like oil price, those in somehow affect our term structure. Right? Term structure. So this is one way to generating, building the model, and see if whether this model provides you more or less reasonable forecast first. Okay. So forecasting, the procedure for that is basically the same. When you estimate this one, and if you determine this is your final model, best fitting model, then choose proc and make model. Here we have many equations, right? Many equations. And we'll solve this in a stochastic way. And we'll put upper lower bounds. And solution is going to be 2011, 10 Q4 to 2012 Q4. Our estimation ends at 2010, the third quarter, right? So let's take this as out of sample, for instance. And the band is 95%. Let's make it, let's say, 67% band. So narrow band. Okay. So it's done. Let's check this output. So level first. F1, upper, lower, and median. Those four. Okay. So up to third quarter 2010, that's in sample, and this out of sample, right? And our sample could be up to 12, right? So these are out of sample, historical, and this is your median forecast and upper and lower bound. Look, this is a forecast. So your forecast was like decreasing and increasing, and then towards some mean. So historical mean could be like somewhere here. Because it's a mean reverting model, and we assume that F1, this sequence is mean reverting. So our guess is like somewhere here is the average. So the forecast is going toward that direction. But it turns out that further decreases. Right? How about the slope variable? F2, high, low, median. So this is actual, and these are band. So look, this is a about the average, and so it's converting to that level, right? Want to take a look at GDP? I want to remind you that these are all short-term forecasts, right? It's meant to be performing in the short term. Oh, your forecast is way optimistic. Right? It turns out this way, right? But probably you are not so surprised. Previously, when we tried to model this real GDP as a single or univariate time series, we recognized that 2000 most of the time, and after this period, there appears to be a kind of trend lower than previous period, right? So we included some dummy here, right? So depending upon how you treat this period in your regression, and also whether you treat before and after our different regime, there could be many different story, right? So this is your first result, and try to interpret this, whether this is acceptable. If this is not acceptable, then you have to go back to your model and here you may want to include some dummy variable, right? Pulse dummy or level shift dummy, right? Level change dummy, right? Those things. So to summarize, estimation, building and estimating VAR is not that complicated one. In fact, it's the same as equation by equation least square to estimate the model, and the determination of P, right order in a VAR P specification. You can choose it by selecting a model that produces smallest information criterion, right? And what kind of variable to include in the model? There is no guide in this method. So when this methodology was introduced early 70s, many econometricians criticized this model as atheoretical economics, atheoretical, not a theoretical approach. Because in discussing this model, there is no guidance to choose which variables or how many variables, how many legs. There's nothing economics, right? But what we include in a vector X is what we conjecture as reasonably appropriate. So if you think exchange rate and KOSPI, stock index, they are, if you guess that they are closely related, then you can include it. Otherwise, there's no guidance, right? So these days, this VAR is considered as the simplest, but often better model than single equation forecasting model. So if you don't know any alternative or better way of predicting variables of your interest, and try this one, VAR, for short period. It will give you more than average performance from our experience. Okay? Much better than univariate series. Why? Think about VAR1 and compare it to just AR1 model for GDP, for instance. Well, even though we know that there is no serial correlation going on in real GDP, but there is a small correlation thing going on, right? Although not significant, right? If we specify that as, let's say, growth rate as AR1, then small coefficient pi, if it is turns out to be, let's say, 0.12, but insignificant, then we know that correlation is going to be 0.12, 0.12 squared, and so on, exponentially declining, right? Correlation. But if you look at actual plot, it's not declining exactly this way. It could be a little different, a little subtle than this one. But if you include, let's say, another variable, second variable in this VAR system, other than real GDP, the correlation structure that VAR model offers you is more complicated than this one. So even though you are allowing small variation, but the correlation structure you are trying to model using either VAR or autoregressive model, there could be big difference. VAR model is much more flexible in that sense. When we come back to this issue next time, people still, I think, among our graduate students, they use this vector autoregression to determine, let's say, what is the effect of changing money supply today on economic growth next quarter and quarters after that, afterwards. We call it impulse response functional analysis. So if we have univariate time series, GDP, we know that we can express this one as an infinite order moving average process and calculate impulse response function, right? But when you have VAR, you can do the same exercise, VMA. You can convert stationary vector autoregressive process as a vector moving average process, but the order is infinity. Then, in principle, you can calculate, using the coefficient to this vector moving average process, you can calculate impulse response function. But the impulse could be from my own shock, but also from others. Okay? So people do that, impulse response function analysis. At the same time, they do something like forecast error decomposition exercise. I'll show you what this means next time, and this one, but I don't buy much of this because many of the results we see from this exercise, well, you can calculate something, but the interpretation is very difficult and often misleading because the model itself is not designed to be, theoretical. It's atheoretical. So use my recommendation is to use this one as genetic forecasting model. I think that's more than enough. But because you have to read someone else's argument, I'll show you what that means next time. Let's see, what else? Of course, much bigger model could be vector ARMA model with P and Q, right? But as I said, because we are extending model to vector dimension, we have too many parameters to be estimated. And also, if you include moving average part, your estimation problem becomes non-linear, very complicated. Right? But we know that as long as ARMA process stationary or VRMA model stationary, you can always find infinite order vector order regression and infinite order vector order regression. And if you work with real data, then usually you don't need to go to that far. Typically truncating as some lag will approximate the system well. So moving average could be entered and you can do it, but many people found that there's nothing much you can gain from make this thing this complicated. So you can see, you can consider this VRP process as a good approximation of underlying, let's say, PQ, VRPQ, VRMAPQ. So let me finish up the rest of the material next time along with this. And to go through this PCA part, I uploaded 2 Gauss codes that do this task. Okay, so next time when we meet, I'll try to spend some time talking about some of the features of Gauss, so that you can use that program for your purpose. Questions? Okay, then that's all I have to say for the day, and I'll see you on Thursday. Thank you.